In this clip, we'll be looking at a classic example from circular dynamics, the bank curve. So let me read the question with you. A car is moving at constant speed on an IC bank curve with a radius r. If we can neglect friction, how do the magnitudes of the normal force and of the force due to gravity compare? We have four choices. Either the normal is smaller than Fg, equal to Fg, greater than Fg in magnitude, or the answer actually depends on the speed of the car. So I encourage you to stop the video for a few seconds and think about it for yourself before coming back to me. Alright, now that you have your answer, let's look at it together. The classic misconception with this problem is that students often think that the car is actually moving on a circle that is on the plane that is like this, as if the center was in here. However, the center is really set in here, so the car always stays on an horizontal circle. It's a little bit easier to see if you think about it in 3D. This is my not very good attempt at making it. So on each side, you have your inclined plane, and the inclined plane actually is happening all around. You can think of this as a velodrome or a NASCAR track. So you have the same inclination all around, and the car would just be moving around it like this, always staying at the same height on the incline. Therefore, the center of the curve is right in the center of that horizontal circle. Now that we understand how the car moves, we can start to think about what's going on in terms of forces. Not surprisingly, the first thing that we should do is really to identify all the forces that are involved in this problem. There's no friction in here, so the only two forces that we'll have to deal with are the force due to gravity and also the normal force. Normal force, we know it will be perpendicular to the surface. So we have something that looks like this, where I will just label the two, force of gravity in here, and the normal force above. Once we have this, the next thing is to think of how we should set up our axes. So we have the choice of the axes, what to do with these. Typically, what you're expecting, when you see an inclined plane, is to have one of your axes that will be pointing down the incline. This is what we did all the time with inclined planes, and the reason we were doing this is that we know that in such a case the acceleration is pointing in this direction. However, in the case of the bank curve, this is not true, because we know that the acceleration of the car is actually pointing towards the middle of the circle. So we're looking for an acceleration that will be pointing this way. And we call this the centripetal acceleration, that I will label AR. Some textbooks are using AC instead. And therefore, it makes sense to take one of the axes and to actually put it parallel to the acceleration. That will simplify our life. This axis that is pointing towards the center of the curve, I'll label R. Some textbooks are sometimes using the letter X for this, but I really like to specify that it points towards the center by using R. The second axis in here is perpendicular to the motion, both to the motion of the car and the R-axis, and we will label this one just Z. Now that we have that, we can think of what's going on in terms of Newton's laws. So not very surprising, we can look at the sum of forces on each axis. We have the sum of force on the R-axis, which will be equal to the mass times the centripetal acceleration, or radial acceleration. Then we also have the sum of the force on the z-axis, which will be equal to the mass times the acceleration on the z-axis. But here we're assuming that the car will be moving in a horizontal circle, so there will be no motion on the z-axis. This means that we know that the acceleration on the z will just be 0. And if the acceleration on the z is 0, this means that the sum of the force on the z-axis will also need to be 0. What are the forces that are acting in here? We have nz, the z component of the normal, minus Fg, and these two will need to be equal to 0. We can see this from the graph as well. If you take just the component on the z-axis of the normal, we know that this component of the normal must be equal in size to the force due to gravity, so that it will cancel it out. So from this value of the z component of the normal force, we can then figure out what will be the length of the normal itself. So it has to have the angle so that it's always perpendicular to the surface, and it will also have the length that is appropriate on the z-axis. So we therefore will have to need something that will look like this. And from that, we have also that the n needs to have an r component that will be pointing this way. Clearly, both from the free body diagram, but also from this equation, we can see that the normal would be greater than fg, because the normal will have to be greater than the z component of the normal. A magnitude of a vector is always greater than the magnitude of the component. And since nz is equal to fg, we get from this that the normal is indeed greater than the force due to gravity. So the answer was 3. I don't know if that's what you got. It's a bit counterintuitive, because when you were dealing with the inclined plane before, you always had that the normal was smaller than fg. The big difference in here is the direction of the acceleration. Now that we understand what's going on conceptually, let's try to put some numerical values in there. So a typical problem when using this setup would be the car is moving at constant speed on an icy banker with a radius r of 100 meter in here, angle theta of 30 degrees, us mu k, no friction, so the coefficients are 0. We can give a mass to the car, 800 kilograms, and the question we're trying to solve is what must be the speed of the car in order for the car to go around the curve easily. So we are just restarting from what we were doing before. We already identified our forces, we have our axes. So the next step is to start back from the sum of forces. So we'll have two equations for the sum of forces. The first equation will be the one we had before, which was that the sum of forces on the r-axis is equal to the mass times the centripetal acceleration, AR. And the sum of the force on the r-axis, there's only a single force that is acting there, and that's the r component of the normal. So we'll have that the r component of the normal is equal to the mass times the centripetal acceleration. The question is asking about the speed, so we know that the speed should come into the question at some point. And where we'll get the speed is really through this quantity AR, because we know that the centripetal acceleration for circular motion is just equal to v squared divided by the radius. So we can use this in the equation if we want to, and we get that in here we'll have mv squared divided by the radius. The other equation is describing what's going on the z-axis. So we have, as we said, that the sum of force on the z is equal to maz, and since there's no acceleration on the z-axis, that was 0, and we got that nz was equal to fg. However, a complication in here is that we need to figure out what nz is equal to in terms of n. So we know it will be the magnitude of the normal times something, a trig function, that will depend on the angle. But what trig function is that? Sine or cosine? It's not super easy to see just from the drawing here. So let me make a page just about that. So to find the angle, we can start from just the incline. And the incline we know in here has an angle of 30 degrees. And on the other side, we have a right angle, and therefore an angle of 60 degrees in here, because we know the sum of the angle inside a triangle must be equal to 180. Then we know that the normal force will be perpendicular to the surface. And I will just extend that line a little bit on the other side for later. And this angle is a right angle, so that will be of 90 degrees. And we know that the other side of the normal, the line that is extending, will also be perpendicular to the surface. So this means that the angle that is in here must be what's missing to 60 to get to 90 degrees. So we know that will be 30 degrees. If we extend the vertical, because remember we want to know what's the vertical component of the normal, that's our z-axis, we have that these two angles are opposite by summit, so this one needs to be 30 degrees as well. That's the angle that we're looking for, because we have that nz is pointing right here. So we can continue the triangle in here and construct the triangle, and we see that the adjacent side to the 30 degree is what we're looking for. So the nz will just be equal to n times the cosine of 30 degrees. That's one way to do it. Another way is just by using an extreme case drawing. So what I mean by that is that we can redraw the same thing, but with an angle that is exaggerated a little bit, that is really tiny, so that we know that we're looking for the angle in here. The normal again will be perpendicular to the surface. So this we know is the case. And what we want is really to find the normal, again, with respect to what's going on either the vertical axis or the horizontal axis. But from the drawing, it's pretty obvious. Do you think that the angle theta would be in here or in here? Clearly theta is super small, so it really can't be this one. So what we will have instead is that the angle theta will be the one that is in here, very obviously from the drawing. Now that we have that relation, we can go and try to look for the sum of forces. So we now know that NR, the R component, will be on this side in here in the triangle, so it's opposite to the angle theta. So we get that NR will be N sine theta, and this will be equal to the mass times the centripetal acceleration, which if you recall was equal to v squared over the radius. On the z-axis, we have that the normal times the cosine of theta will be equal to Fg. Fg is just the mass times the acceleration due to gravity. So just as we found previously, we get that the normal is equal to mg divided by the cosine of theta. Since cosine of theta is always smaller than 1, we can see that n indeed will be bigger than mg, just as we discussed in the conceptual part of the question. Now we want to take this expression for the normal and just replace it in the equation that we had for the sum of force on the r-axis. So we get mg divided by the cosine of theta, which is just normal, times the sine of theta is equal to the mass times v squared divided by the radius. What we're looking for is the velocity, so we'll try to isolate it. Right away you can see that the masses will cancel out. So this means that our solution will actually not depend on the mass. So no matter what would be the mass of the car, we would get the same velocity. That would just depend on the angle, the radius, and the value of g. That's it. So simplifying, bringing r on the other side, we'll have r times g sine theta over cosine theta. That's just a tangent of the angle theta. And we know that this will be equal to v squared. So if I take the square root, I will get that v is equal to the square root of r times g times the tangent of theta, which once we put the numbers in will give us 100 meters times 9.80 meters per second squared times the tangent of 30 degrees. And doing the calculations, you see that meters times meters over second squared. So we'll have meters squared over second squared, square root. We indeed get meters per second. That's good. And doing the math, we'll get a value of 23.8 meters per second. So this is the speed of the car. And as discussed, it depends only on r, g, and theta. That's it. Now the question I want to ask you as a follow-up is, what would happen if the car was actually going slower than that? So if the car gets into the curve with a slower speed than 23.8 meters per second, there's still no friction. So what will happen? Again, I encourage you to stop the video and try to think about it on your own for a few seconds. Then come back. Alright, so let's look at this. We have to think about what stays constant. So we know that the mass, the acceleration due to gravity, as well as the angle will not change. But if that's the case, this means that that is constant, and that term is constant as well. So if all of these are staying the same, this means that n does not change either. And if the normal does not change, and we have that again theta does not change, and m does not change, this tells us that AR is also constant. And if AR is constant, this means that we have just one possibility. If V decreases, then we know that the radius must also decrease. So if the car comes into the curve with a speed that is too small, what will happen is that the car will actually move a little bit down the incline so that it will readjust the value of the radius in order to get the same centripetal acceleration as it had in the first place. Thanks everyone. Hope this helped.